Hello guys, today we are going to start you a new topic about the nonlinear system identification. Okay, because the nonlinear system identification is the main tool of the what the are present or the physical systems. You know, in the real world, everything is related to what the nonlinear system, because we don't have the any linear system. We may approach to linearization on the nonlinear perspectives, and so we can drive the any system with a specific points or the equilibrium points of our algorithms. Okay, but so what happens if we are using the nonlinear system? Okay, and so we have the title of the nonlinear system identification. We have progress about how we can utilize or build this system. Okay, and so in this note or in this lecture, two forms of system will be discussed in order to get the system parameters by using the system identification tool. As in the previous lesson, we have talked about we may approach the proper values of the A and B or the system parameters, but we don't have the exact values of these things. Okay, because if our progress or the error function or the cost function is minimized by our algorithms, and then we cannot approach the proper or the exact values of the A and B. Why? But we may approach. Okay, and so that's sufficient to control the any systems, but we don't have any knowledge about what is the exact values of the A and B. We may improve our methods in order to obtain these exact values. Okay, and so firstly, we should introduce our system like this one. Let's have a system like the easy one is that we have firstly x dot equals to minus a times x square plus b times u. Okay, and so x is measurable right now, and a and b are the physical parameters of our system, and so the dynamics can be affected by these terms, and u should be input value in here, and so we can apply any input to drive the system any points of our algorithms. Okay, and so also we should give the x0 value in here, because if we don't have any initial condition in here like this one, and so we cannot iterate the system by using our iterative algorithms. Okay, and so what about our objective is that the unknown A and B is present here. Okay, and so what will we do? In here we may propose any other system like this one. X hat dot is equal to the minus a hat x hat square plus b hat times u. Okay, our proposition model or the suggested model looks like it. Okay, but we should revise this model in terms of we should add the stabilization term in order to stabilize or goes to the infinity or the zero value to the x, and so when t goes to the infinity, and then this x hat value should be minimized or goes to the zero. Okay, and so in order to collect all the terms in here like this one, we should write about this function proposition in here. Firstly, x dot should be reorganized by using the minus am times x plus am times x minus a times x squared plus b times u. These are the real physical systems. And so if I add the minus am times x and plus am dot x and never change in these equations. But if you have the another system, x hat dot is equal to the what minus am x hat, these are stabilization term to what you goes to these derivative terms to the 0. Okay, and so x hat value goes to the 0. Okay, and this is called the stabilization term. And so as well as we should add the am minus x value in here, because we subtract this term by using these coefficients, and x hat dot can be selected by arbitrary equations. Okay, only if we need to what to minimize our cost function. And also we should give the minus a hat times x square plus b hat times u. Okay, our system can be selected by using these terms. Okay, and so this suggested model should be revised by using these coefficients. Okay, and then what? We should drive, or we should define the estimation error in here, like this one. The estimation error can be E1 is equal to the what? X minus x hat, and so x measured, and this is the estimated values of the what? The measured values. And so we can take the derivative of this term, E1 dot is equal to the what? The x dot minus x hat dot. And so we can involve this x dot dynamics values of the our physical system and our estimation model. You should remember that this x hat dot value is running on the what? The microprocessors or the computer architecture, because we don't have the only power of the what? The reorganizing and resetting the whole the values of this suggested model. These are the physical system, remember that. Okay, and so we can write the E1 dot is equal to the what? A m times x plus a m x minus a times x squared plus b times u, plus or minus in here, I'm sorry, minus in here, and then minus a m x hat. Okay, and so the minus a m times x plus a hat x squared minus b hat times u. Okay, these are the proper form of the what of our algorithms. Okay, but okay, this should be minus, should be replaced with the plus 1, and then we can collect the whole the terms into the what? E1 dot is equal to the what? Minus a m x minus x hat, because these terms remove each other, and so we can collect these things in here, minus 1 parenthesis, and so minus a m times parenthesis x minus x hat should be given here. And so this removed and this removed, and then we have also a hat minus a x square minus b hat minus b times u, coming from the equation of these things. Okay, and so these are the proper form of the what of our algorithms in here. And so this should be assigned the estimation value of a estimation, and this can be reassigned the b estimation in here. And so this is given by the equation form E1, and then the last final equation is equal to the what the E1 dot is equal to the minus am times E1. This also stabilization term in here, because am should be selected as the positive value in here. And so also we have the a estimation times x square and minus b estimation times u. This is the proper form of the what of the R selective algorithm, or the minimization degree, or the dynamics of the R algorithms. And so if we properly minimize the E1 value, selecting by the Lyapunov function in here, and then we can obtain the proper values or stabilization values of the A hat and B hat value, which are the closest values of the what the physical and the parameters of the A and B. Okay, in the next lesson we will talk about the stability rule relates to what the E1 or the estimation error function. Okay.